We've already taken a look at limits of infinity, but let's start looking at limits at infinity. What I mean by that is that we're going to determine the limit of a function as x approaches infinity. We've already looked at f of x equals 1 over x a lot. We've seen that the limit as x approaches 0 would mean that if we're coming from the right side, we expect that limit to be infinity. But when we come at it from the left side, we expect it to be negative infinity. And since those two things are not the same, that limit does not exist. Now, when we're talking about the limit as x approaches infinity of f of x, what we're saying is that given a point, we want to move this point along this curve so that its x-coordinate is going to get larger and larger and larger, so it'll move out here. And what we see, of course, is that the larger that the denominator gets, the smaller the overall fraction gets. Now, it's never going to actually become 0. It's never going to become negative, but it's going to get very, very small, infinitesimally small, so small that it approaches 0. And so the limit as x approaches infinity is 0. Similarly, if x is going to approach negative infinity, it's going to go out towards the left. And this curve also, now it's going to go up. Its absolute value is going to get smaller and smaller and smaller. But again, it'll approach that x-axis and not ever get there. So that limit is also 0. We've also taken a look at 1 over x squared, and we saw that its graph changes. This is the graph of 1 over x. But when we have 1 over x squared, what was negative now becomes positive. And that just means that the limit as x approaches 0 now is going to be infinity. However, those limits as x approaches infinity are both going to be 0 because they approach that x-axis on either side. So what about when we're dealing with a function like f of x equals x over x squared minus 4? It's a little bit more complicated, but it's got to fall in the same idea as these 1 over x's and 1 over x squareds. Now, we could graph this function and evaluate the limit that way. We could set up a table and evaluate the limit that way. But I want to show you how to do this using algebra. What I'm going to do is I'm going to rewrite this fraction. And I'm going to do it by multiplying the numerator and the denominator by the same expression. That expression is going to be 1 over x squared. The reason that I want to do that is in the denominator. When I distribute that 1 over x squared inside, x squared divided by x squared will give me 1 right here. But then we'll still have 4 over x squared. In my numerator, x divided by x squared is 1 over x. Now, how that is helpful for us when we're trying to evaluate the limit is now I can rewrite the limit as x approaches infinity of f of x as the limit as x approaches infinity of 1 over x over 1 minus 4 over x squared. And I already know how 1 over x acts. And I already know how 4 over x squared acts. That as x approaches infinity, 1 over x is going to turn into 0. And 4 over x squared is going to turn into 0. So that means that this limit is going to turn into 0 over 1 minus 0, which is 0. This is actually why the graph of f of x looks the way that it does. Remember, if we were going to graph this, first we would factor it completely so that our denominator was x plus 2, x minus 2. And we said, as we go through this, that there are 3 important numbers. They are 0 from the numerator. That makes the function equal 0. And then negative 2 and positive 2 are going to be asymptotes because they make the denominator equal 0. Then we went into the whole sign chart thing. Negative, negative, negative would be negative, and this thing's going to alternate. And we're ready to graph. And we said that there is also going to be an horizontal asymptote that is the x-axis, because the degree of the numerator is smaller than the degree of the denominator. Right? And we just said that, and that was our whole reasoning for it. But the actual reasoning on why we get that horizontal asymptote there is because of the limit. That the limit of f of x as x approaches infinity, is going to be 0. So that means as x gets way out there, it's going to be positive, but it's going to approach 0, that x-axis. That's why the x-axis becomes an asymptote for us. Right? Similarly, as x approaches negative infinity, f of x is also going to be 0, which is why we have that horizontal asymptote on that end as well. But through the magic of division, or multiplying the numerator and the denominator by the same fraction, we can use this technique to help us find these limits as x approaches infinity. So when I'm looking at g of x is equal to 6x plus 9 over 2x minus 1, what I want to do is multiply the numerator and the denominator by the same thing. This time, I'm going to multiply it by 1 over x. When I do that, distributing the 1 over x inside, we'll have 6 plus 9 over x. In the denominator, distribute that inside, we'll have 2 minus 1 over x. So when it's time to evaluate the limit, that's the same thing as taking the limit as x approaches infinity of g of x, which we just rewrote as 6 plus 9 over x over 2 minus 1 over x. Then take the limit of each term. When we evaluate this limit, 6, as x approaches infinity, 6 is going to stay 6. But as x approaches infinity, 9 over x will turn to 0. 2 is going to stay 2. And 1 over x is going to turn into 0. So this entire fraction will be 3. We see that as kind of a rule that when we have the numerator and the denominator with the same degree, we can just kind of, it goes back to just simplifying those leading terms. Now we have h of x, where that degree in the numerator is larger than the degree in the denominator. We can still use this trick to help us out. Right? Multiplying, I'm going to multiply by 1 over x. Right? When I do that, I'll end up with x plus 3 plus 2 over x. In the denominator, it'll be 1 minus 4 over x. Now we can take a look at that limit. The limit as x approaches infinity of h of x. Well, we just wrote h of x as x plus 3 plus 2 over x over 1 minus 4 over x. Evaluating that limit now, going term by term. As x gets infinitely large, x is going to turn into infinity. 3 is going to stay 3. 2 over x turns into 0. In the denominator, we have 1 minus 0. So infinity plus 3 is infinity, and infinity divided by 1 is infinity. I want to point out that whenever I'm using this method of multiplying numerator and denominator by this fraction, my whole purpose is trying to get this leading term of the denominator to be an integer. That way, all the other fractions are going to turn into 0, and I'll have an integer in the denominator. I won't have 0 in the denominator, so I'll actually be able to divide by a number. Sometimes what'll happen, in the case of when the numerator has a degree that's larger than the denominator, we'll also end up with this x in the numerator. It's that x that ended up turning into infinity, and that limit will always be infinity whenever the numerator has a larger degree. In fact, we've got 3 different scenarios that involve the degree of the numerator and the degree of the denominator. If the degree of the numerator is smaller than the degree of the denominator, something like 1 over x, for instance, as x approaches infinity, that limit is going to be 0. If the degree of the numerator and the degree of the denominator are the same, something like x over x, the limit as x approaches infinity, those two would cancel, and we'll be left with some constant. In this case, it's 1. But the important, how you would actually do that is just simplify those leading terms. And then if the degree of the numerator is larger than the degree of the denominator, something like x over 1, Well, as x approaches infinity, this entire fraction would also approach infinity. Here I have a whole bunch of limits. Let's quickly go through all of them and evaluate their limits. Let's start with this limit. As x approaches infinity, of 3x plus 4 over 6x squared plus 1. It all comes down to the leading terms. All right? The degree of the numerator is smaller than the degree of the denominator, so that limit is going to be 0. As we move over to this limit, as x approaches infinity, of 3x plus 4 over 6x plus 1, so not squared anymore. All right, those degrees are the same. Look at those leading terms, 3x over 6x. All we have to do is simplify the fraction. Those cancel. 3 over 6 is 1/2. Let's move over to this one. Limit as x approaches infinity, of 3x squared plus 4 over 6x plus 1. Now when we look at those leading terms, we see that the degree of the numerator is larger than the degree of the denominator. So we're back at infinity. Continuing on. Limit as x approaches 0 of 3x plus 4 over 6x plus 1. We're going to jump right to here, but look out. The limit isn't going to infinity anymore. We should always be paying attention to that x as well. All right? As x approaches 0, actually these two terms both approach 0 here and here. But we'll have 0 plus 4 in the numerator, 0 plus 1 in the denominator. So this entire limit is actually just 4. Pay attention. We see that limit. X is not approaching infinity. So we're going to let x turn into negative 1/6. And 3 times negative 1/6 is going to be negative 1/2 plus 4. Negative 1/6 times 6 is negative 1 plus 1. We have this situation with 0 in the denominator. We'll have 3.5 in the numerator, 0 in the denominator. This is going to give us one of those limits that it does not exist. And last one, 3x plus 4 over 6x plus 1 again, but we're going to let x turn into 4/3. So 3 times 4/3 is 4, plus 4. 4/3 times 6 is 8, plus 1. So that limit's going to be 8/9. Okay? And that's how you can run through a bunch of limits fairly quickly. Pay attention to two things. What we're taking the limit of, as well as what we're letting x approach. If x is approaching infinity, then we pay attention to degrees. Right? If x is approaching 0 or any other integer, then you're going to just try and plug things in. If you end up with that number over 0, it does not exist.